Yesterday we looked at T results which turned a trig integral into a polynomial, whereas trig substitutions is sort of, I guess, kind of the other way around, where we turn an algebraic statement, so a polynomial type thing, and we turn it into a trig integral. And so basically what we're dealing with is things like this, where in the integral you've got the square root of a squared plus x squared. And so you want to make use of the trig identities. So you think of which trig identity says 1 plus something squared is equal to something squared. Which one is it? 1 plus tan squared is sec squared. So you see square root of a squared plus x squared, then you try, well, let's make x equal a tan theta. Then I can turn those two terms into a single term using trig identities. That becomes a trig integral. If we had a squared minus x squared, so this time think of one that says 1 minus something squared. Yeah, so it's the rearrangement of the sign, or the cos, as you say, you can pick either. So a sine or a cos. And then if it was the other way around, if you had the trig squared minus 1, yeah. So we'd use sec, because it's the rearrangement of the 1 plus tan squared. So that's the idea. This is one of our standard integrals we saw before, and we already know what the answer to this should be. We see 1 over the square root of a squared plus x squared, and we of course know it is equal to... Well, let's go and prove it using this trig substitution. So it's a squared plus x squared. So I'll use x equals a tan theta. So dx will end up being a sec squared theta to theta. Sub that all in, so the dx a squared sec squared. A squared plus a squared tan squared becomes a squared sec squared. The square root of a squared sec squared is a sec. The a's cancel, so it's just the integral of sec theta. And we know the integral of sec is the log of sec plus tan. Now of course that's got thetas in it. How do I get x back in there? Well, x is a tan theta. So I just draw myself a little triangle here. There's theta, x on a. The hypotenuse, not a coincidence, it turns out to be that square root. So sec theta, reading off the triangle, sec is reciprocal of cosine, isn't it? So hypotenuse over adjacent plus opposite over adjacent. Now, you might be thinking, hang on, didn't we say it was just x plus? What's this on a? But remember, a is a constant. So it is the right answer, because I could use my log laws to say that's the same as minus log a, which I could just put in the constant. That's all plus a constant. X on 1 minus x squared. So 1 minus, that was the one where we used either sine or cos. What did I go for? I've gone with the sine. So dx becomes cos. Subbing in, I've got sine theta, cos theta, square root of 1 minus sine squared. 1 minus sine squared is cos squared. Square root of cos squared is cos. Cos will cancel with the cos, leaving us with, there we go, sine theta. So just integrating sine theta. Integrate sine minus cos. Again, let's draw up a triangle so I can see exactly what that is. And the other side. Cos is adjacent over, so I just get minus 1. Now, hopefully, if you got that question, you wouldn't do that. Hopefully, you would have a look at the numerator and see, oh, x, that's kind of like the derivative of the denominator. We've actually got du on root u there, or a fraction of du on root u. Square root of x squared plus 3. Okay, so trig squared plus 1, that's the one where we're going to use... oh yes, isn't it? It's tan again. I just had the x in the other spot. So root 3 tan theta, dx root 3 sec squared theta to theta. So we've got square root of x squared plus 3. So that becomes 3 tan squared plus 3. 3 tan squared plus 3 is 3 sec squared. Square root of that, root 3 sec, times the dx is root 3 sec squared. I end up with that wonderful integral that we love doing, sec cubed. So I've got 3 lots of sec cubed. Now sec cubed, of course, we do via... Okay, let's do it. We split it up. Sec theta times sec squared. I'll make u equals sec theta. To u is sec theta tan theta. To v is sec squared. V is tan theta. So I've got 3 lots of sec theta tan theta minus 3 lots of the integral sec theta tan squared. We change the tan squared. Now, remember, if we're treating this like an equation, I'm not looking at the first line equals the last line, because of course the first line's got x and the last line's got theta. I'm looking at the third line equals. So I've got 3 lots of the integral of sec cubed. Of course, after I do the substitution back in, I've done the substitution first. Let me explain. If I had moved the theta over, I've got to be real careful, because it's going to be 6 times the integral. Now, I would have to write that as a separate line, because I'd say 6 times the integral equals. But remember, we're trying to find 3 times the integral. So you still only divide by 2. So you might find it easier, and that's why I've done it here, you might find it easier to substitute in first before you move it over, and then it becomes a little bit more obvious, because when I move the square root of x squared plus 3 over now, it clearly is 2 lots of the square root of x squared plus 3. And then divide both sides by 2, and we eventually have our answer. I haven't underlined yet. I wonder why. What do you reckon I'm going to do?
I'll put the log stuff in.
Yeah. You don't have to, I suppose. It's still the same. It's just a different constant at the end of the day. Alright. 2e.